Hey, this is Annex, and this tutorial is going to be a continuation of the last one. So in the last one, I broke down what is a sine wave and how that relates to sound. And why does that matter? Because when you modify the formula, you modify the shape of a sine wave, and when you do that, you can change the amplitude, so the height, or the frequency or the pitch. And with both of these things, so with amplitude, we're measuring loudness, so how much gain, how much, is the change in air pressure density that this sine wave creates. And when we're measuring frequency, when we're modifying that, we're talking about the pitch. And then we talk about the waveform density, so how close together are the oscillations. So today in this part, I'm going to go a little step further back into the math of this and how this makes sound, going from this to sound. And I also have a Serum wavetable open here. So this is what one sine wave sounds like. And these Serum wavetables are nice because you can combine different graphs, so different formulas for different types of sine waves, and then Serum adds them, or samples from each of those. It's like adding them on top of each other, and it comes out with a really cool dynamic and harmonic complex sound. So that's why Serum is so cool to use for this stuff. But first, I will tell you why it does that, scientifically more or less. Let me find my pen. Okay, whatever. So when we look at air pressure, here I have some diagrams for you. So last time we looked at this oscillation. So we started with the y equals sine x, and we just saw it move over time. So the x-axis is time, the y-axis is amplitude, and this is the waveform moving as it's generated by your computer. So when it's generated by your computer, it's digitally, so you can make all of these graphs and patterns with zeros and ones and just with this sine function. And we also saw if you can increase the oscillation by a factor of 2, so meaning increase the pitch, or decrease the pitch by a factor of 2, so make the wave length longer instead. Now, the reason why we're interested in this is because you can add these three sine waves on top of each other. And that's what you can do in Serum with this. It's called additive synthesis. So basically making wave tables or resulting waveforms by combining different graphs with each other. And what this is showing you is one period. So this is 2 pi. So think of this as like a circle. You just like cut in half and spread out this way. So one oscillation is 2 pi, meaning one time you go around in a circle. But this might help you to understand it a little bit more because this stuff isn't really intuitive. So here we see those 3 graphs, so with different amplitudes, so different loudnesses, and we combine them, it looks like this. So we're taking the positive amplitude creates even further gain in amplitude. So when we're going to stop that. So the blue here is the resulting waveform that we have from these 3 waveforms on top of each other. So when this blue goes up like this, it's constructive, so meaning because all the amplitudes are positive at this point, it adds them together, basically. And it does the opposite when it's below, so when it's -1, when it's negative. And when we're down here, we're talking about negative air pressure, and up here we're talking about positive air pressure, or air density, I guess, of the sound wave. So that's why we look at these 3 different graphs, is because we can synthesize different waveforms by them, just basically by layering them on top of each other and seeing what the resulting waveform is. So if we played all of these outs at the same time, we would hear the same as if we just played this resulting waveform. And if you think about the last example I gave in my second last tutorial, so this would be like having these different waveforms that I showed you. So these were for a bass, a male vocal, a violin, a guitar, and a flute. So on each of these rows, on each of these tracks. And then I recorded them to audio. So this is the resulting audio waveform. So what the signal looks like, how the waveform was shaped, and how it goes over time. So remember, we have amplitude is the height of one of these, and frequency is the density, so how frequently it oscillates. And these are what the waveforms look like of those instruments independently. And then we combine them here. So we have the constructive or destructive relationships between the different waveforms, depending on if they're basically above or below or the opposite and canceling each other out. So I won't go into that too much more, but the reason that we do this is to make sounds, and we can make complex harmonies by combining the sounds of different instruments. So of course, all sound is made in this way, but you can think about it in terms of individual tones or sine waves, in terms of wavetables, in terms of instruments, or in terms of like combining all of these together, so in like your final song. And when we combine these ones together, it sounded like this. And here we're hitting at a lot of the different frequencies, so a lot of the different pitches. So you can see that in the frequency spectrum. And we're also hearing it at different levels, so at different decibel gains that we see on the left here. So this is the frequency as we are looking at it over time. Okay, so I'm going to break down a little bit why this is oscillating, because we also talk about oscillators and things a lot in electronic music, and it's the basis of synthesis of sound. So what does oscillation mean, and why does it matter? So this is the 2D representation of the creation of a sine wave, but we can also look at it in 3D. So this is what is happening when you have just a typical sine wave. So this would be like the y equals sine x that I drew here. So we have this oscillation going literally in a circle. It's oscillating, meaning like moving in a circular fashion. And the sine wave is created here. So on this box here is the sine wave. And we can also make cosine waves, but we only care about sine waves for music because these are, longitudinal waves. And I believe the cosine waves are transverse, which means they still do create movement, but you can't make movement through a gas, which is air. So as I mentioned, sound and music is just different air densities and pressures moving through air. And that's what creates, what we hear with our ear, the differences between that. So this is what it looks like in 3D. And if you don't completely understand that, don't worry too much. But I'll break it down a little more into how it looks like in the waveform and why that matters for you. So here's what we're actually seeing. So this is like, remember this? So this is just our sine wave. This is oscillating over time. And what it's doing with the air is this. So every time it makes an oscillation, so going from the lowest to the highest to the lowest air pressure in one cycle, whatever its cycle is, it's creating differences in air pressure. So on the top here, we see how the air pressure is actually changing with respect to what that sine wave is doing. So this is called sound pressure. It's the same as amplitude, and it's low on the bottom and it's high on the top. When we think about looking at a speaker, so like a subwoofer or whatever, when you see it moving, so when it moves in, when music is playing, you're seeing an area of low pressure here, so negative pressure, and that's at the bottom of this. So I think it's called the trough or something of the waveform. And when it's pushing out toward you, so when you actually hear the like boom of sounds, it's the peak here. So this is how we see when it's peaking here. So when the audio waveform is at its highest, this is where we have the highest air density. So this is the air up here, and this is the movement of the waveform as it creates air density. And think about it in the same way as I showed you in this figure. So this means that, so amplitude is how loud we hear something, as I explained to you in the last tutorial. But when we're here, we have different degrees of pressure. So the pressure is what's created at this point, and at this point, and at this point. But here is going to be a lot higher pressure. So this is 4 times higher pressure than if something were, a quarter of that amplitude. So when you have a higher amplitude, you create more pressure within these peaks, and then you create more influence on the air molecules and a louder sound. So here's another way to look at it. So this compression, so this is the same as this last video we saw. It's just static, and it's showing you how the pressure here, so this area of high pressure is in this compressed area, and the area of low pressure is in this refracted area, so in the area of least pressure. So in amplitudes this would be -1, and the positive area of pressure would be +1, basically, if you're just using a typical sine wave where it's 1 to 1. And again, this is oscillating over time, so it's moving according to the waveform and from the time it's produced. So this is also what I just showed you. So this is how the amplitude works. So see this waveform at the top? It's a lot bigger, so it's a lot taller than this waveform at the bottom. And when the waveform is a lot taller, it makes more pressure, and it makes these high pressure areas, and then we hear something is louder. Whereas this is kind of a lower pressure area, and it would be lower. So amps, it's not 1-to-1 related to decibels, but it's the same idea. So I actually tried to work it out for you, but it got too complicated and then it wasn't worth explaining. But just know that the amplitude, so the gain, is the same idea as decibels. It's the same as loudness, more or less. And this is why it happens. And this up and down motion, so with our computer, because we're making electronic dance music, this is created by the generation of ones and zeros according to this sine wave pattern by our computer. So it's taking electrical or digital energy and converting it to physical energy. So that's why we measure things in negative decibels in our DAW. So see here, it's in always negative decibels, and it maxes out at 0 decibels. And 0 decibels is a human-made number, and that just means anything over 0 decibels we can hear, decibels, and anything under we can't hear. But for the purposes of production, anything under 0 is kind of like imaginary because it hasn't been turned into physical sound yet. And the amp, so the gain on that, think of it as like a guitar amp. So if you turn the amp up really high, it's going to amplify that signal and make it louder, so making the waveform a lot bigger, which creates more loudness. Okay, so now I'm going to talk about pitch a little bit. So this is a typical piano roll on a standard piano. I think it has 88 keys. And for each of these keys, so each of these notes, it corresponds to different frequencies. So we have low frequencies on the left-hand side. That means less oscillation, so fewer cycles per second in the bass notes, and higher frequencies or higher oscillation or higher pitches on the right-hand side, so for the treble notes. And we can use this to understand the combination of various waveforms with respect to actually what makes something harmonious or not. And you can go pretty deep into the theory on this, but I will try not to do that because that's what other people do, and that's not really what I can contribute here. So how do you change what you see, or how do you go from here to actually to a note, so to a pitch value? Let me go back to this handy little website, and you can also go to this website by yourself and play around with this. What we see now is not useful for us if we're going to see what a waveform synthesis is, but what is interesting for us is when we use this formula. So when we use this formula, so y of t, y of x, so the vertical axis, the y-axis, is a function of the amplitude multiplied by sine with this function in it. So sine of 2 pi, so 2 times 3.14 basically is just a factor, times the frequency in cycles per second, times time in seconds. Someone also said I should edit my videos a little better, but yeah, I'm not here to entertain you. I'm here to just teach you something that I hope that you're interested in. You can watch other YouTubers if you want better production quality. Okay, so we can see how do these waveforms interact with each other by looking at a tool like this. So remember, this oscillation is what we see with this circle on the left here, and it means the center of mass. So imagine you take a rope, a really heavy gym rope, and you throw it like this. The center of mass is what it's moving. It takes the energy over the cycles, over the oscillations. So we want to influence what the center of mass does by modifying the equation, so modifying this equation. So because sound is really happening very quickly, I'm going to zoom in. In the other tutorial, we figured out that 200 beats per minute is 300 milliseconds. But harmonies are created at around, say, like the, I think, 6 millisecond range. So we have to zoom in a lot more to see that. So you can't see the oscillation anymore, but just know that it's still happening. And I also reduce the amplitude a lot so we can, investigate this a little better. Okay, so what I drew here, get rid of those. So what I drew here is this blue graph. So just ignore the amplitude for now, because I'm only talking about the frequency. So amplitude you would just control with the gain or reduction on our DAW, but the frequency is what actually is affecting the waveform right now in terms of harmony and pitch. So this, I've drawn a graph of what would be A1, or a low A. So this is a frequency of 55 hertz, so 55 cycles per second. And going back to this graph, so this would have us somewhere about here. Yeah, here. So this is about 55 cycles per second for your low A here. So it's a slow waveform. But what I can also do is add the A 1 octave up and 1 octave up and see how that makes a harmony. So see how those work together. I'm not going to use this anymore because I think this is horribly confusing. I'm going to use this, which I posted on my website. So this is like a cheat sheet where you can reference the pitches, so the notes and their octaves, according to MIDI. So this is actually what you're putting in your DAW. Not what actual other standard would be. So this is just for your DAW use. So here I'm going to show you what 55 hertz is, what 110 hertz looks like, and also what this will be 220 hertz looks like, and how the waveforms interact with each other to make that. Okay, so this is our first graph. So this means that our amplitude is 0.001, and we have a sine graph with a function of 2 pi times the frequency, which is these 55 hertz, times time. So this time is the x-axis, and because sounds are really, really, really small, this is like, yeah, this does one oscillation in 0.018 seconds. So yeah, these things are happening really, really quickly, but that's what makes it sound. So what does it look like if we go one octave up and draw the A with a frequency of 110 hertz? That multiplies the frequency by 2, so it makes it twice as fast. It means it's oscillating twice as quickly, and it has a pitch that's one octave up. So when we look at the green here, that's how we see it oscillates twice as quickly. So this hits this one full oscillation. It goes up and down and back to 0 again in half the time as the blue one does. And let's do that one more time. So let's add with 220 hertz. I don't know why it would make that the same color. Okay, so the 220 hertz is twice as fast as that. So it's 4 times as fast as that 55 hertz, and it's going to be one octave up again. So this is just showing you what an A note is doing at one octave up twice. So this 55, this is going to be the fundamental frequency. So if this were the first note you press, this would be A, and then it oscillates at different frequencies after you press it. And it does that because it's a combination of all of these waveforms. So if we go to combine them, you basically just add them on top of each other. So then we have a function that is just adding 3 different sine equations. I'm just going to add this one at the end. And this is our resulting waveform. So this is showing you the harmonics of playing A at 3 different frequencies. Sorry. So if we go back to here, we're playing this A at frequencies of 55 hertz, so A0, 110 hertz, A1, and 220 hertz, which is A2. And when we do that, it resonates, it oscillates in the way that this graph shows us. And we can see that they're harmonious with each other because they intersect at even intervals. So this intersects at 0 here, at 0 here, and yeah, it's just a very beautiful, symmetric, nice graph. In hardcore and frenchcore, you can make some really nasty waveforms, and that is also beautiful, but in a different way. So I won't talk about that now. Just going back to your DAW, so if this isn't too hypothetical for you. So the reason why we learn this stuff, or why you can learn this stuff, is so you can apply it to your music production. So like when we look at kick like this, like when I was using in my tutorials, we see really low frequency oscillations here. So these are more the bass notes because it's a longer frequency, so fewer oscillations per second. And here we have more density, so it's higher oscillations per second, and also some saturation, which adds like harmonic compression and distortion. And then we have, again, like a lower frequency here. So when you're looking at these waveforms, what I was doing here was comparing it to a kick, to another kick. Oh, that's gone now. Anyway, so when you look at these, when you look at a waveform, you should already be able to get an idea of how it's going to sound in terms of its loudness and its pitch. Sorry, that was really loud. So with this is obviously a kick, but if we listen to this flute, is going to be completely different. So it's going to have lower amplitude, so it's going to sound quieter to us, and also a higher frequency. So you're going to see more, more oscillations per second, in the waveform here. So that's why it goes up and down more than this longer bass. So this is actually at 55 hertz in this kick. Just a second. And we can see that with G-Tune. So this is free and it's on my website. Yeah, you should go download it because you can pitch anything. So see what the fundamental frequency of anything that you're playing is. I mean, you can also do it by going through this frequency spectrum, but it's nicer to have this little tool. Whereas, so we saw that was about 55 hertz, and we can go to our spectrum analyzer and see that as well. So see the highest point here is the first big point is the fundamental frequency, meaning we press the key of A, and we did that in our MIDI when we generated this. But we also have these remaining harmonics here. So because that A is still oscillating and still vibrating with other sounds that give it this interest in the higher octaves. And if we go to the flutes and look at G-Tune for that, it's going to look completely different. So here the fundamental frequency is almost, it's at A4 here at like 880 hertz. And it's a lot denser here because when we go to the treble octaves, we have higher frequencies, which literally means more oscillations per second. So you're going to have more energy going on here. And that's why, bass waves, so bass sounds travel further. And bass is also not directional. So that's why the neighbors complain at DEF CON because they feel the bass. They don't necessarily hear it, but they feel it. Because when you have these higher frequency stuff, they have so much energy, they lose this energy quickly to the air around them. And when they lose it, then they stop vibrating more quickly. So these bass waves are, they're why you actually feel something pounding, because they have a lot of energy in them, but they're also a slower wave. So I hope you found that useful, and I hope it didn't get too technical for you. Let me know what you thought in the comments, and let me know if I can explain anything else to you about this. I think I was going to do a tutorial on harmonics more specifically, but let me know if you'd like anything.